Let me think now about light. Light is an even more difficult story. It's a more difficult for a good reason. The good reason is the following. Waves have a wavelengths. Sound wave, depends on the pitch that you're listening to, but sound waves have kind of a typical wavelengths of the human scale. A few centimeters, kind of the size of your ear, probably not by a coincidence. Probably not by a coincidence. Because of that, we can notice effects such as the one I described with the speakers. As you move from side to side, you can move your ear a distance that is comparable with one wavelength of the sounds. If you want to go from a place where the two waves are out of the phase to a place where the two waves are in the phase, you have to move basically one half of the wavelengths. If the wavelength is human scale, it's easy to do that, and you hear loud here, soft here, loud here, right? So it's a pattern in the room. With light, it turns out is that the wavelength is very, very small. It's less than a micrometer, and because of that, the sunlight wiggles move. The slightest wiggle would move you from one peak to top and then to the another peak and other trough. I'm sorry, so let me repeat that again. So with light, it turns out is that the wavelength is very, very small. It's less than the micrometer, and because of that, the slightest wiggle would move you from one peak to low, and then to the another peak and another to low. You would be washing out this effect. You wouldn't be able to stand at one place and obviously tells what that. It wouldn't be silence now. It would be darkness, and then brightness, and then darkness, and then brightness. Think about how spectacular and weird that would be if there were two light bulbs in the front of you and you could move your eyes to some spot where all of a sudden they cancelled out. That would be an amazing and direct proof that the light is a wave and not light is a bunch of the particles coming out of the light bulbs. You've never seen that with your ordinary eyes with ordinary light bulbs, and nobody had seen that back in history. That's why people were arguing so vehemently about whether the light is a particle or wave. Isaac Newton believed that the light is made of the light particles, that a light bulb is emanating little light particle in all directions, and it's not a bad hypothesis. I can give you some argument why you might want to believe that. Remember, I said that the waves bend around the corners. The evidence for that was that you can hear a sound behind the door even though you cannot see that sound marker. However, you can't see a person behind the door unless they are straight through the door. The light is not bending around the corner. That seems to be evidence that the light consists of a bunch of the little particles. Now, it is also true about waves that the smaller the wavelengths, the less they tend to bend around the corners. You can check this with water waves of the different wavelengths. The bigger the wavelength is compared to the opening, the more bending you tend to have. It's not a proof that the light is a particle, but there was no evidence back in the Newtonian days that light is a wave. Isaac Newton was thinking about other properties. He was thinking about color. He was thinking about the path of the light rays through the optical elements, and so this argument was kind of the philosophical argument for him. He didn't have an experimental equipment required to show convincingly, once and for all of that light is a wave or particles. Although he had his belief and articulated them, they didn't really matter for the science that he was doing. It was in the one, Thomas Young did this dramatic experiment that I just described, where you have two light bulbs and you can find a spot where they cancel one another. Young shows to the world that light really is a wave. It's very much like that speaker experiment, and what he needed was very high precision. It was a challenging experiment. Here is a basic idea. Young took a very, very bright light source, then he ran it into a black wall in which he had cut a very, very narrow little slit. One slit to let the light through. When you let light through a very narrow light slit, it's narrow enough that it goes down to the distance scale of the wavelengths of the light, then the light will come through the slit just like a water going through a little slit. It looks like you have a point source, and the light will come out in all directions. Now you have the equivalent of the point-like source of the light, and if you were to look at that slit, you would see this little point-like source of the light. The light is going out in all directions. You can tell because it's illuminating the wall on the far side of the room uniformly, and it does become a little bit dimmer and dimmer as you move farther away. But that makes total sense whether you believe that the light is a bunch of the particles or that light is a wave. So far, no proof either way. Light could be a little particle going through the slit, bouncing every which way, like a particle bouncing off the edges, scattering and going in all sorts of directions. We haven't yet proven that light is a wave, but now on the back wall that's uniformly illuminated, let's put two slits. It's called Young's two-slit experiment for this reason. Now, think about the light that's striking those two slits. They are symmetrical with respect to the first slit. There are waves fronts heading outward, and where nowadays I would think of the electric field. When the electric field is high, at one point if you go anywhere along the wave front, the electric field will be high and then low, and then high and then low. I'm visualizing this as a water wave where the high spot is expanding in the nice, beautiful spherical pattern, reaching to the two slits symmetrically. So these two slits are now in the phase, right? When one is up, the other is up. When one is down, the other is down. Now, Young has no idea what's moving. He has this sort of vague idea that it might be a wave, and it's a wave. He thinks something is moving. We'll come back to the point. Whatever it is, wave go positive and negative, and so now you have two light sources, two slits, which are coherent. They are in sync or in phase. Wow. Now, go on to the first side of the two slits. Turn around and look back at them. You see the two little bright spots. Let's consider the two hypotheses. If light is a particle, then you have a little particles spewing out of the one hole and little particles spewing out of the second hole. It is back to my argument that is, if you have particles coming at you from two places, you are going to see them no matter where you are. As you move farther and farther away, it will become dimmer and dimmer, but basically you expect a pattern that the highest, brightest light behind the slit and the fading off smoothly as you move off towards the edges. That's what I would expect if I believe that the light is particles coming through the slits. If I believe that the light is a wave and that the wave are coming out of the slits and they are starting off in the sync, then there should be places back on the back wall where, for instance, if it's equidistant to the two slits, then they both started in the sync and they are waving towards me and still in the sync. So I will see a bright spot, but if I moved off to the side a little bit, if I moved just far enough that one of the waves has gone half a wave further than the other, half a wave means when the one is up, the other is down, and vice versa, down, up, up, down, down, up, up, down. They are cancelling. They are destructively interfering with one another, and there is a darkness. With my eye, I would be looking at these two bright streets. Then I moved over a little bit, and now I cannot see the street. Then I move over a little bit further, and I see them again. It's remarkable. It's hard to imagine, but it's absolutely correct. That's what you see in the laboratory. Wow! You could take a piece of film and develop it, and you'll see the bright band, then a pitch black band, and then bright band. Right. It's called an interference patterns, and it is as clear as signal that you have a wave as anything I can think of. It's very, very dramatic, and the pattern is completely predictable from the wave model. I can tell you how far apart bright and dark should be. It's geometry. When do the waves add up? When do the waves cancel? I can also predict what happens if I change the color of the light, because that would change the frequency of the light and therefore the wavelengths. Wow, wow, wow. I should be able to make a concrete mathematical prediction about how the pattern spreads out, or narrows a little bit if I change the color, or if I change the distance between the streets, or if I change the thickness of the streets. Many experiments, all of which are completely compatible with a wave model for light. Wow! So cool. As you think about all of these extensions and consequences, you realize that the wave model of light is convincing to the point that you accept it as the truth about nature. That's what we mean when we talk about scientific truth, is that in experiment after experiment, new situation and completely novel situation, they all match up with this one simple hypothesis. By 1801, people know that the light is a wave. Newton was wrong. That's a big deal and very exciting for Mr. Young to be able to show that Isaac Newton is wrong about something. Physicists love to be able to show that one of the great heroes has made mistakes, and because this is the way science progress, right? And as every revolution in physics, this one took a little bit of time. It was written up by Young in a way that some people found a little bit hard to understand, a little bit hard to believe. It is a pretty dramatic experiment, and so other people had to repeat the experiment. These verification and the extensions had to be checked, but it was a pretty quick revolution, at which point there was a huge puzzle. It's clear to everybody that the light is a wave, but what is waving? As we talked about over the last few lectures, it took another 60 years until Maxwell in the 1860s demonstrated mathematically that light is indeed a wave. Wow! It's an electromagnetic wave. It's not some material substance that is lifting up or moving backward and forth. It's not a physical motion. It's electric and magnetic fields which are waving in the strings, stronger, weaker, stronger, weaker. Once you have understand that light is a wave and sound is a wave, you can start to take advantage of it. I mentioned those sounds cancelling headphones and the lovely little invention. Once you know that the sound is a wave, there is this clever idea. Suppose you are in the airplane and there is a drone from the engines. It's a very steady low frequency sound wave striking your ear. You build a little headphone that produce another sound, those sounds cancelling headphone are producing a loud sound as loud as a jet airplane at the location of your ear. Wow, it's a very loud sound they make, but they are monitoring the jet sound, and when the jet pressure waves is high, they emanate a sound wave which has a very pressure, and vice versa. They cancel the outside noise by adding their own interference noise, and it's quite spectacular that you can do that. They work pretty well. They work best for the steady outside drones that aren't changing with time, so that you can steadily create your own wave that cancel exactly with the outside wave. You can do this with light as well. Anti-reflective coating is just a simple design that takes advantage of the fact that the light comes and bounces off of the front or the back. Both ways, you are going to have some sort of interference of the two different paths. You can make that interference cancel out the light which is in the middle of the visible range, and so you won't have a strong reflection. Wow! The wave model allows us not only understand the nature of these things, light and sounds, but it also allows us to build our devices and design new experiments. In the long run, it's very powerful to be able to separate a wave from a particle, and it helps us to understand how we think about different things in the world much more clearly.